So for this theory seminar, we're very pleased to welcome Thomas Celora and Peter Hammond, who are graduate students at University of Southampton in England, working with Niels Anderson, and also with Greg Comer, who is local to us in St. Louis. And so Thomas did his undergraduate at Milan, and then went to Southampton briefly via the Bryn-Haskell zone in Warsaw, and is now working with Niels on general relativistic fluids. And Peter Hammond is a final year PhD student in Southampton, and he's also interested in binary neutron star mergers, particularly on composition and reactions, things that have been of interest to us here in St. Louis. And so we're very excited to hear what Thomas and Peter have to say on this. So thank you both, and we look forward to your talk. Oh, and I should also say that for questions, this is a small enough audience that I think we can allow people to raise their yellow hand in the reactions and ask a question during the talk if they want to. So please feel free to do that. Okay, thank you.
Yep, right. Thanks for the introduction and also the invitation. Let me start first of all sharing my slides. So no, yeah, I can see the people in the chat, so I should be able to see you if you raise your hand, but just pick up in case you need to ask him something. Right, so today we wanted to present you this recent work that I've done together with Ian, Pete, Nils, and Greg, which is about formulating bulk viscosity for neutron-star merger simulations. And the idea is that we will start by simply formulating the problem, namely describing how do we think about modeling a fluid that is undergoing nuclear reactions and how this is linked to bulk viscosity. Then we will introduce the ideas of the multiscale methods and try to explain why they can come to our help when we consider the issue of resolution limitation. And then we will try to assess what essentially what we need to do, what's actually relevant for a real numerical simulation. So the idea is that we want to kind of share the job of presenting this work to you, basically because I've worked mainly on the theory aspects of the thing, and Pete has done the simulations. And so before we dive into these talk, we decided that it was kind of nice to start with showing you some results of some actual simulations that Pete has done. And so I think I'm handing it over to Pete because it's better for him to discuss this instead of me.
Yeah, so I think the main idea is to give some context to the sort of conditions that you expect to see in neutron star mergers, which informs how we're thinking about bulk viscosity in the reactions. I know a lot of people here aren't familiar maybe necessarily with what goes into and what comes out of a neutron star merger simulation. So we'd just like to give you an idea here of the sorts of temperatures and densities that we're looking at. So the two left-hand figures are taken from a simulation in 3D. So these are 2D slices of that at the point where the two stars first sort of make contact with each other. And then the two right-hand figures are from 5 milliseconds later. So once the kind of remnant object has started to settle down a little bit. So if you look at the top left-hand, so the temperature panel on the left-hand side, what you can see is that most of the cores of the two stars are cool. So in an ideal world, they would still be down at sort of a very low zero temperature, but numerics kind of forbids us from doing this. So you kind of see the very cold cores still, but you have this artificially heated atmosphere around the stars, which is anywhere up to about 10 or 15 MeV. But you can also see that the interface between the two stars, so in the center of the figure, there's this sort of sheet of very hot matter. So that's anywhere up to about, I mean, this particular simulation, it was up to about 75 or 80 MeV. But I think anywhere up to about 100 MeV is what you could reasonably expect to see in a merger. And then if you look at the temperature on the right-hand side, so after the remnant has sort of formed and settled down a bit, you can see that there is still a very small cold region towards the center of the figure. So where the temperature and the YE bits meet in the middle, there is a small region that's still quite cool, but surrounding that is quite a big chunk of matter that's sort of in the 25 to 30 MeV range. And then you also have these two hotspots, which are formed from the sheet of matter that collides between the two stars. It gets pushed out to the sides, and then you see this sort of two blobs of matter, one on each side of the star at around sort of 60, 70 MeV. So those are the sorts of temperatures that we sort of see in these things. And then if you look on the bottom two figures, you can see the density on the left-hand side of each one. So this is rho over the nuclear saturation density. So the highest densities we see are in the region of 4 to 5 NSAT, and that covers most of the kind of the cores. So before the merger, you'd probably be sitting around 3.5, and then in the post-merger remnant, it gets a little bit more dense as the whole thing starts to settle down, up to about sort of 5 NSAT. You can also see sort of wispy bits of atmosphere coming off. So we kind of have to cover densities down to about, so here we're at 10 to the minus 6, but we sort of have an artificial atmosphere that encompasses the whole domain that's about 10 to the minus 8 NSAT. So those are the kind of density ranges that we have to deal with our simulations. Then if you go on to the next slide. So yeah, so this is, so this simulation uses just an advected YE. So the composition of the fluid element was essentially frozen with the initial data in beta equilibrium. So that means this mu delta would be 0. So this mu delta is the imbalance between the neutron, proton, and electron chemical potentials. So we freeze the composition in each fluid element and then allow that to evolve. And so you can see that as we reach merger on the left-hand side, the big sheet in the middle is up to quite a big distance, I think, from equilibrium, so about 150 MeV, which is quite a lot, but the majority of the stars is still around about equilibrium. And then on the right hand side, you can see that as that sort of sheet gets forced to the edges of the stars and then kind of flung out into space, a lot of the domain ends up sort of out of equilibrium. But it's important to highlight here that there are no reactions going on here. So this is kind of a worst case scenario, if you will, in terms of getting matter to go out of equilibrium. And that was kind of what we wanted to study here, was if you had no reactions, how far out of equilibrium could you get? So we can see here that we do get quite far from equilibrium. So reactions are something that we need to think about. There's a couple of questions. I don't know what order they appeared in. So VJ, I don't know if I'm pronouncing that right.
I was just wondering, you're showing all these simulations, and I wasn't clear about what was involved. What were the assumptions of your model?
So we use the APR equation of state. It's a fairly vanilla kind of thing. It's been around for a long time, so that kind of gives us the pressure and energy relations in the fluid. But then we have, as I say, we have an advected YE, so we assume the matter consists of neutrons, protons, and electrons. We then use this YE parameter to say, well, how many of the baryons are protons, even though we call it YE, because we're assuming charge neutrality, the number of protons and the number of electrons has to be the same. So YE tells us what fraction of the baryons are protons, and then we advect that along with the fluid element. So that gives us effectively a simulation with no reactions.
Thanks.
And Alex?
Yeah, just a quick question. So on the left, what's the time scale on which you get this far out of equilibrium? How long does this, I mean, I assume the stars start in equilibrium before they touch.
Yeah.
This is exactly 0 milliseconds. So how long does it take to get that far out of equilibrium?
So there are sort of, as the stars get closer and closer together, they kind of, they shed some of the outer matter. So you end up with this region in the middle that tends to be quite far out of equilibrium to start with. But then as the two stars collide, which is sort of on the scale of less than a millisecond, that's when you get to see sort of not insignificant densities actually ramp up to this kind of deviation from equilibrium. So I'd say it's probably order milliseconds, if not less.
Okay, thanks.
Right.
Yeah, did you want to carry on?
Okay. Okay, so as after these very nice introductions by Pete, I think that it's fair to say that an important ingredient that still need to be added to the simulation technology is that of reactions. Because what we have done, what people have done so far is mainly implemented these ideal fluid equations, if we forget about magnetic field stuff, which essentially boils down to these set of equations here. There is an equation for the energy continuity. There is the Euler equation here that tells us that the fluid for velocity is proportional to the pressure in the gradient in the pressure. Then there is the baryon continuity, and to close this system, we use an equation of state that's tabulated, for example, in the composed database that give us the pressure as a function of, say, the baryon number density, energy, or temperature, and this electron fraction. But as Peter has already said, as already told you, because in these equations here, there is, say, no information about the reactions, we can essentially evolve to two limits. The so-called slow limit, where we assume that the reactions are so slow that the matter composition is frozen and it's advected along with the fluid. And the opposite limit, the fast limit, where we assume essentially that the reactions are so fast that matter has time to relax towards chemical equilibrium at each point in time during the evolution. And from these, well, you can kind of clearly see that the modifications that we have to make on the fundamental equations that we are evolving in order to add reactions are, from, say, a theoretical perspective, fairly simple, in the sense that instead of evolving and advecting the electron fraction, as Pete has done in the simulation that is shown you, one just have to put a non-zero reaction rate on the right-hand side. And so essentially change this equation here with an equation like this. Now, this is true, but there are some problems that arise when essentially the reactions that you want to actually implement are fast, in the sense they are faster than the timescale that you can capture using the simulation. And to kind of intuitively see why this is a problem, well, the idea is that if you consider, for example, the advection equation, and you work out the dispersion relation that tells you that, you know, the waves propagate with a constant speed. But if instead of considering, say, the continuum limit, and you take its finite difference version, well, you can see that the finite difference introduces some sort of numerical damping that kills off whatever happens on timescales or frequencies on frequencies of the order of your inverse timescale, which is shown by this plot here. And so, just to give you some numbers, say, the best grid spacing that is obtainable today is of the order of 10 meters, which corresponds to a timescale of the order of 10 to the minus 7 seconds. And so essentially the idea is that whatever, everything that happens on timescale shorter than this is damped and killed by the numerics. This is also the reason why there has been quite some effort, I would say, recently that has been put into this idea of subgrid modeling. So trying to somehow capture the effects on the large scale dynamics of what happens at the subgrid scale. So at the scales that you cannot represent numerically. Now, how does the bulk viscosity enter the picture? Well, the idea is that you can introduce the affinity, which is from the thermodynamics perspective, is the thermodynamic conjugate quantity to the YE, the electron fraction that I was talking about previously, which is a quantity that, as Peter said, measures the distance from chemical equilibrium. And for example, for the simplest kind of realistic model of neutron-star matter, so the NPE system, neutrons, protons, and electrons, can be defined like this. And the definition can become more complicated if you add finite temperature effects or the fact that neutrinos are trapped, but essentially the structure of the equations remain the same. The numbers will change, but the structure is the same. And once you have an affinity, you can also work out an evolution equation for the affinity, which typically would look like this. So you would have a time derivative of the affinity, a term that drives the relaxation towards equilibrium, so the fact that essentially this affinity goes towards zero, and then a source term, which involves this theta here, which is the expansion rate, so the forward divergence of the fluid for velocity. And if you take an equation like this and you assume that you are in control essentially of the density oscillation, because the expansion rate is telling us that what is driving the system out of equilibrium is the fact that the fluid element is undergoing some compressions or expansion. If you assume that you are in control of these oscillations, of the frequency of these oscillations, then an equation like this will give rise to resonance plot of these form, a frequency, or equivalently a frequency-dependent bulk viscosity. And you might recognize this plot as it's taken from one of yours paper, actually. Also, if you've got an affinity, you can also, if you've got an equation like this, you can implement this, at least formally, via the Israel-Stewart type equations. Namely, you can introduce a bulk viscous pressure, which is essentially given by the corrections to the you expand the equilibrium around, you expand the pressure around equilibrium, and the bulk viscous pressure will be essentially the first order corrections. And you can essentially write down an evolution equation, which essentially would look like the affinity equation here. This is all nice, but from the numerical implementation perspective is quite problematic for different reasons. Well, the first point is that is the stiffness problem. So because the bulk viscosity is meant to represent the effect of the reactions, it's kind of intuitively clear that the relaxation towards equilibrium, which is given by essentially this parameter A here, will be on the same time scale with which we expect the reactions to happen. And so if we have problems representing numerically the reactions because they are fast, we would have also problems in representing the relaxation towards equilibrium via an equation of this type. Also, it is important to mention that because the expansion rate acts as a source term, but the expansion rate in a nonlinear numerical simulation is not controlled by us, is linked to everything else, to all the other equations in the system. So for example, through the Euler equation. And this makes it complicated to implement numerically. And the third point is that if you are implementing on the bulk viscosity via an Israel-Stewart prescription, you are implicitly or explicitly assuming an expansion around thermodynamic equilibrium, which, as we have seen from Pitt's simulation, might not be guaranteed to be valid, at least not over the entire computation domain or over the entire merger. Another thing that one can think of by looking at this resonant plot here is that if you are able to capture what are the main frequencies that are, not main, the frequencies that are excited during the merger, one might use one computation like this to estimate the value of the bulk viscosity coefficient and then use that value to evolve in time. Now, this is also not really viable numerically because essentially we cannot reconstruct the frequencies on the fly. And this essentially boils down to the Gabor limit, which is some sort of it's essentially the Heisenberg principle, which tells us that we cannot localize in time and frequency a function, okay? A function cannot be time limited and frequency limited. And so if we want to associate, say, a frequency at a point in time, because our numerical time step is of the order of 10 to the minus 6, 10 to the minus 7, then this would mean that we would like to localize with an uncertainty of 10 to the minus 6, 10 minus 7 second at frequency. And this would correspond to an uncertainty in the frequencies of the order of 10 to the 5 hertz, which is 100 times, 10 to 100 times the frequency that we expect to be the main frequencies that are excited during the merger, because 1 to 10 kilohertz is the frequency with which the two corresponds of each other, essentially. So we cannot do that. One thing that we could think of doing is to take a Fourier transform on some window of time around this time, say T naught, at which we want to associate one or a bunch of frequencies. This would be also problematic for different reasons. The first one, is, at least to me as a theorist, is that it would kind of raise issues with causality, because you would have to integrate both over the past and future of the fluid element word line, which is not nice. And it would also be, I would say, computationally very expensive, because you have to evolve the simulation, stop it, go back in time, perform the Fourier transform, evaluate the frequencies, and then update the value, say, of the bulk viscosity coefficient and evolve again in time, which is, so essentially doing something like this would be problematic from the causality perspective and also computationally very expensive. But even if we, say, ignore these problems, it won't be possible essentially to localize frequencies precisely, because there will be some leakage into adjacent, say, frequency bits. And this is shown by this plot, this schematic plot that we have done here, where you have this signal, say, in green, which we made, and it's made out of, say, 5 frequencies. And then you can also see in the top panel different window function, the same window function but with different widths. And in the lower panel you can see the power spectral density, which we would be using in order to reconstruct the frequencies. And as you can see, it won't be easy to localize precisely what the frequencies are. And also the reconstructed frequencies will depend on the shape and size of the window function that you choose. It's entirely up to you. So I don't think it's really trustworthy in this sense. And as a final point, maybe, I want to just mention that this signal here is a signal with 5, say, constant frequencies. We expect, though, to have, during a merger, to have frequencies that are, say, evolving in time, and the situation gets even worse in that case. So essentially reconstructing the frequency does not seem to be a viable option. So what else can we do? This is the point, I think, where multiscale methods can come to our help. And to see that, we can essentially rewrite the equations, the same equations that I was showing at the very beginning, the energy, the Euler, and the baryon continuity equation, plus the equation for the electron fraction. But this time write them down in non-dimensional form in order to bring out what are essentially the timescales, the parameter that tells us the timescales with which the quantities evolve. And as you can see here, essentially the energy, the fluid velocity, and the baryon density evolve on the same blue timescale, while a priori the electron fraction evolves on a different timescale, the red timescale. And so the point is that if the blue and red non-dimensional parameter are of the same order, then we have to evolve the full system. And we might also get away with that because we know what are the typical timescales with which the hydro variables, so the energy, the fluid, and the baryon continuity evolve. And so in that case, there would be no problem maybe in evolving the electron fraction directly. On the other hand, if say the red parameter is way smaller than the blue parameter, then the electron fraction would be evolving on way faster timescales, and this would be problematic computationally. But in that case, we can rely on to these multiscale methods, which essentially allows us to start from a set of equations where you identify some slow variables and some fast variables, and then you work out an approximate set of equations, essentially integrating out the fast degrees of freedom, okay? And by integrating out the fast degrees of freedom, you can work out an approximate set of equations such that the solution to the approximate set of equations is guaranteed to converge to the solution of the true full set of equations when the limit within red, when in the limit for red way smaller than blue, essentially. So, yes.
Can I quickly ask a question, or just try and clarify something?
Yes.
So the epsilon st, the blue one, that is saying basically how quickly is stuff happening compared to the resolution, the time resolution scale of the simulation? Is that what that's saying?
It's just a non-dimensional parameter that you pick up when you introduce some reference energy, some reference fluid velocity, and so on, and you bring out all the dimensional bit and you put them together, you recollect them, and you pick out this number, which is the Struhl number.
I guess I'm wondering what it means, because I think, so the epsilon A, the red one, what that seems to be saying is, yeah, how quickly is beta equilibration happening compared to, well, it's giving you some time scale, right? It's giving you some, that epsilon A, it looks like it's got dimensions of time here, right? It's actually not dimensionless the way you've written it, right? Because it's...
Well, it's dimensional because, so I've been, in a way, I've kind of followed the tradition in being sloppy, in the sense that when you non-dimensionalize the equation, you start from, say, a dimensional time, you introduce a different dimensional time, which would typically indicate, say, for example, like tilde t. And then after you have recollected all together the dimensional terms, you redefine your time. So this time is a non-dimensional time.
Okay.
And therefore, so this A is dimensionless. But fine. Yes.
So that non-dimensional time, what time scale have you chosen to be 1? Is it the resolution of the...
Can I jump in, and I think I can answer this. So effectively, so the Struhl number gives you the dynamical timescale of the fluid, and this epsilon A gives you the dynamical timescale of the reactions. Because we're trying to simulate the fluid, we assume a priori we can properly resolve this Struhl timescale, because otherwise, what the hell are we doing? So I think that the point that Thomas is making is that if these two timescales are of the same order, then we know that we can resolve the reaction timescale because we know that we can resolve the Struhl timescale. But then obviously if the timescale is much shorter, then we maybe necessarily won't be able to resolve it because we know that our simulation will cut off at some timescale shorter than the Struhl timescale. Does that make sense?
Yes. So I agree. Obviously, if you have to make your simulation good enough to catch the relevant fluid flows, and if the reactions are happening on that time scale, you're bound to catch them. So the only problem would be if they were happening much faster than the fluid dynamics. If the re-equilibration dynamics was much faster than the fluid dynamics, then you'd have a problem. So is that what you're saying?
Yeah, and then this is
essentially.
Okay, all right.
Go on, Pete, maybe you had something.
No, I was just going to say this is where the multiscale methods comes in, is when we know that A is too fast, then we do this trick with integrating the timescale out and getting some approximate form.
Yeah. So essentially, if you use this multiscale method, you get rid of the electron fraction variable. And what we have shown is that the approximate equations that you're left with are equations that describes a single fluid with a bulk viscous contribution to the pressure. And this bulk viscous contribution to the pressure is of the Navier-Stokes type. And this is shown by this schematic plot down here, where you can see, say, in blue, the full Israel-Stewart behavior of the affinity, and in orange, the dashed orange is the Navier-Stokes limit. So what this plot is saying is that for low frequencies, where low means low with respect to the reaction timescale, so these essentially this red A here, the two prescriptions are the same. The two prescriptions are identical in the infrared limit. While if we start looking at around the resonant peak and to the right of it, the two prescriptions start to be different and diverge. But this plot is also showing you another important thing, which is schematically this gray area here. This gray area represents the frequencies that we don't have access to numerically. And as I tried to convince you at the beginning, there will always be a gray area like this because of the finite differencing. So the question is whether or not this gray area covers the resonant peak. If the gray area covers the resonant peak, then we have access also only to the frequencies to the left of the resonant peak, which would, because the resonant peak is at omega equal A, so a frequency of the order of the reaction timescale, it would mean that we have access only to frequencies that are way smaller compared to the inverse timescales of the reaction. So we cannot evolve the reactions, we cannot evolve the electron fraction. We can, though, use the multiscale methods and implement the effect of the reactions via bulk viscosity of the Navier-Stokes type. On the other hand, if the gray area is not covering the peak, then yes, using a Navier-Stokes type bulk viscosity is kind of clearly wrong, as you can see immediately from this picture. But at the same time, because the resonant peak is at omega equal A, that would also mean that you have access to the frequencies or the timescales with which the reactions happen. And so in that limit, you don't really have to implement a bulk viscosity. You might want to implement the electron fraction equation instead, because that is computationally simpler. So I think that the bottom line is that we need to understand whether or not the reactions are fast and decide what to implement if they're fast or not. But fast with respect to what? Fast with respect to the timescales that we can resolve numerically, okay? Now, up to now, the discussion has been mainly, I would say, theoretical, with the exception of amazing plots. So now we are back to some kind of real simulation stuff. And so we have tried essentially to estimate where and how high the peak, the resonant peak that it was showing in the previous plot is. And we have done that using the APR equation of state, because that's the equation of state Pete was working on with the simulation that he was showing at the beginning. We've also have checked what happens if you use the slide 4 equation of state, and surprisingly, the results don't change. We are not claiming that it's model independent at all, but it was nice to see that. And so what are these two plots showing? Well, the plot to the left is showing you where the peak is. So it's plotting this calligraphic A, which tells you the reaction timescale. And on this plot, you can see a bunch of contours. The two bottom ones represent, correspond, say, to frequencies between 1 and 10 kilohertz. And so these are the frequencies and the timescales that you would need to be able to resolve if you want to simulate a merger, because that's the frequencies with which the two neutron-star cores bounce off each other. So if you cannot see that, well, then you're stuck essentially. This dot dashed line instead represent the time step that it's the current best time step, and the dotted line instead represents the time steps that we essentially think that we will get down to, or within a timescale of 5 to 10 years. So how do we read this plot? If you focus on one contour, say this one that represents the situation nowadays, if you look at a point in this phase space that is below that contour, that is a point where reactions are slow enough that the simulations can capture them and can resolve them. While if you take a point above the contour, that's a point where the reactions are fast, so fast that you cannot capture them numerically. And so are the regions above the contour where you might need to implement a bulk viscosity of the Navier-Stokes type, because you cannot implement the reactions directly. The plot on the right-hand side instead is telling you how high the peak is. And essentially what we are plotting is the maximum bulk viscous pressure contribution over the equilibrium pressure. And so the dark areas in this plot are the areas where essentially the maximum contribution to the pressure of the reactions is expected to be essentially negligible with respect to the equilibrium contribution. And so you might just want to get away implementing an ideal fluid evolution. While the regions in this plot that are, say, yellowish / orangish are regions where the maximum bulk viscous pressure contribution is not negligible with respect to the equilibrium pressure. And so you would need to at least take the reactions into account to see whether they actually make an effect in practice, make a difference in practice. This plot has also the contours obtained from the plot on the left-hand side overlaid. And so what we can see by this plot is essentially that both nowadays and in, say, 5 to 10 years' time, we expect to find regions that are in the parameter space that are exploring a merger where the reactions are actually relevant and are expected to make a difference. But we also find regions where the reactions not only are important, but are slow enough that we can capture them. And also regions where the reactions are important and fast enough that we cannot capture them directly, okay? And also what this plot is also telling us is that, improving the numerical resolution, there would be less and less need of relying on the bulk viscosity approximation, because you can implement more and more the reactions directly. We have also estimated the contours using a different estimate, essentially. So we have used the opacities that are typically used in radiation hydrodynamics scheme. And so you can essentially work out an equilibration timescale using the neutrinos opacities, working out an energy averaged opacity. And then from that energy averaged opacity, essentially multiply it by the speed of light, and then you get the inverse timescale. And so what we are showing you here is the comparison between, say, the contours to the left computed using the APR equation of state, and the contours to the right that are computed using the neutrino opacities. Now you can see that the two contours are different, and I would say that they are in a way expected to be different because of the many approximations and that go into the estimates. So ideally, in the ideal world, if we were able to put in all the relevant physical information into the actual estimate, ideally these two contours, the two contours, the one to the left and the one to the right, should agree, but they're not. At the same time, it's also quite reassuring that the general qualitative conclusions that we can draw from this are the same, because also these plot to the right tell us that there will be regions in the phase space explored in a merger where reactions matter and where the reactions can be captured numerically directly. There are also regions in the phase space explored in a merger where reactions matter or are expected to matter, and we cannot capture them directly, and we will need to rely on a bulk viscosity approximation of the Navier-Stokes type. Okay, so to kind of conclude, the take-home message is reactions are hard to implement because the timescale varies over many orders of magnitude in different regions of the parameter space. A possible way forward that came out from this analysis would be to have a code that is able to transition between a description in terms of the electron fraction and a description in terms of a Navier-Stokes bulk viscosity on the fly. It's important to flag also the possible conflict/interaction with the large eddy filtering technique aimed at modeling the subgrade effects, because as we have discussed in the paper, essentially is filtering that enters at least implicitly in the implementation would give rise to an effective reaction rate or an effective bulk viscosity. And so this effective reaction rate or effective bulk viscosity can counteract, can balance, or can enhance the real reaction source, say bulk viscosity, for example. It's also important to mention that it's not entirely clear to us how hard it is to implement a code that is capable of transitioning between the two prescriptions. And also, I also wanted to mention this double counting issue, because if you assume that you have, say, the set of reactions, and part of these reactions are slow enough that you can resolve them, and part of them are fast enough that you cannot, well, after these 40 minutes of discussion, you might think that now you can, say, capture the slow reactions directly and model the net effect of the fast ones via bulk viscosity. Yes, that might be true, but that is probably true, but you need to tread carefully, because the multiscale methods show us that if you integrate out, say, the fast reactions, then these would affect also the reaction rate of the slow ones. So you need to take that into account as well. And well, that wasn't really the conclusion, because we wanted to conclude with essentially trying to answer the question, why should we care? And this figure here shows you why should we care. But because this figure is Pitt's, then Pitt is the person that should discuss it. So back to you again, Pitt.
Yeah, so effectively what we have here is two simulations. So in one of them, we run the simulation as before with an advective electron fraction, so no reactions. But as Thomas mentioned on one of the earlier slides, you can also take the opposite limit for the reactions and assume that everything is always in equilibrium everywhere. And so that's what we do for the other one. So what you can actually see here is the gravitational wave signal from the post-merger remnant sort of ring down, if you want to call it. And what you can see is that the two peak frequencies are actually noticeably different. And so the red curve on this plot is the expected noise curve from the Einstein telescope. And you can see quite clearly these two peaks poking above that noise curve. And what that means is that if you want to do something like template matching or anything like that, parameter estimation, using the Einstein telescope, you will need to include these reactions properly in your simulation that gives you the waveform template. Because the two limits are different, reality is going to sit somewhere between the two. Maybe it's almost entirely on top of one of them or the other. We don't know, because no one's really done this before. So all we know is that it's going to be somewhere between the two. But as I say, the point is not to claim that we know the truth of where the peak will be, just that the two limits are different. So you need to do the whole thing properly, basically.
Right.
How far? Sorry, can I ask a quick question?
Yeah.
How far away is this merger? Like, is this a really nice event?
So this is a very well aligned 40 megaparsec. So this is if the pole was pointed right at your detector, but 40 megaparsec is where we saw 170817. So it's not a ridiculous distance to claim.
Okay, but it's one of the better events. Like we
you
don't
would
expect
have you would have to be lucky But the point with this is that because the frequencies are different, as long as you catch enough signal in the detector, you really don't need a lot of signal to noise to tell the difference between these two. So we calculate this parameter called the mismatch, which is so it's effectively, you can think of it as a dot product of the two waveforms in frequency space, and then you take one minus the size of that. From that mismatch, you can kind of work out the signal to noise of the difference between the two signals. And so with this, you can see that I've put on there that the required signal to noise is 1.2. So you'd only need a signal to noise of 1.2 in order to tell that these two signals are different. Obviously, the more signal to noise you get, the better you could resolve this. But essentially, because this required signal to noise is so low, if you're going to see these two signals, you're going to know that they're different.
Okay, but I have to see them first. That was my question.
Of course, you have to see them first. Yeah.
Okay.
But I don't think it's unreasonable to claim that you should see these with a third gen. Obviously, second gen, you don't see anything after the merger, really. So this is kind of irrelevant for that. But as people are sort of now starting to move towards the kind of Einstein telescope, cosmic explorer type stuff, this is becoming relevant, I think.
Okay, thanks.
Okay. So is your talk complete? Is that the end?
Yep.
Okay.
I think so.
Yeah, that was the end.
Okay. Well, so thank you. Everyone
Kind of end on the end, but the end.
Okay. Yeah. Everyone can do their little yellow applause hands or whatever it is they prefer to do. Okay. And are there any questions that anyone would like to ask? I see all different yellow things, but Vijay, did you have a question? Maybe not. I'm not sure if Vijay had a question or not, but okay, maybe he's got a different hand up there. Let's see. Anything else anybody wanted to ask? I can ask a question. Okay, and Alex. Oh, Alex, do you want to go ask a question first?
Yeah, can you go back to, I think, page 9? I'm not entirely sure if I understood what's going on here. So what kind of assumptions do you make for the neutrinos on the left and on the right? Like on the left, when you talked before, there were no neutrinos at all, right? So
yeah. So the left is just calculated. The contours are calculated based on the rates that come from one of your papers for modified Urca. So calculating that out of equilibrium, or that might have been Mark and Stephen. I can't remember exactly which paper it was, but we found somewhere some functional form of the rates around equilibrium. You can take derivatives of that, and that allows you, with derivatives on the table, to calculate this A. And then the color map is just from derivatives on the table.
Okay, but for the left, you have to assume that neutrinos are either always free streaming or always trapped, right? And then obviously on these temperature scales, they do both of these things and everything in between, right? Yeah,
the formula we had is just for the modified Urca, so and it's just for the modified Urca on the Fermi surface. So you're essentially just doing this at 0 temperature and ignoring the direct Urca at the.
Right. So I think it's assuming that neutrinos escape even when the thing is hot enough, so they really don't. It's pretending that they escape. Okay, yeah. So what's going on with the right-hand plot? I wasn't so clear about that either.
So in the right-hand plot, we used a piece of software called NuLib, which allows us to calculate neutrino opacities. So you can take the absorption and scattering neutrino opacities and construct an equilibration opacity, which is effectively 1 over the expected mean free path of the neutrinos. Because you know the mean free path of the neutrinos and you know that they're traveling at about c, that gives you some equilibration timescale for the neutrinos.
So I guess but I mean, neutrinos can have different kinds of events in their lives. You know, they can scatter off stuff and not do anything much, but if they can scatter off a neutron and not do anything much except, you know, their path is interrupted, or they can turn the neutron into a proton.
Yeah.
You know, so
yeah, so this is why you use this combination of absorption and scattering capacities that Thomas is highlighting down at the bottom.
Okay.
So if you ignored all the scattering, kappa equilibrium would just be equal to kappa absorption. But because you've got a bit of scattering, you're effectively lengthening the distance that the neutrinos are traveling in some sense, because they're bouncing around off everything. So you get this, what they call an equilibration opacity. So, which is sort of 1 over the true mean free path of the neutrinos, effectively. So this, because that then allows you to construct a timescale, you can then say, well, these two measures are in a very roundabout ways measuring the same thing. They're measuring how long it takes this system. Obviously, there are different assumptions going into each system, but it's how long this system takes to relax towards equilibrium.
Okay, I guess, okay, we could pursue that in more detail, but maybe that we should not make other people wait while we do that. So that one other thing I wanted to ask about, if you go back to your slide with the resonant hump and the gray, you know, the gray area. Yeah, so I guess what you're saying is that, so really that gray area doesn't, well, okay, O'Neill cited a comment. The neutrino plot is constructed following the prescription from the most recent work of Radice et al., which aims to... Okay, right. Right, so in this, roughly speaking, I think the way I could think about it is that the gray-white boundary stays in the same place because you have roughly the same resolution everywhere. And I know that's not exactly true, but roughly that's true. And as the, depending, as the density and temperature varies, that blue hump moves up and down, right? Because because the rates are changing depending on whether things are hotter or denser or not. Right? That's a rough way I can think about it. Is that right? Okay.
I think so.
Okay. So supposing that we get to a place where it's very hot, and so the reactions are happening very fast, so the blue hump moves well into the gray zone, right? So in the white zone, where you can resolve what's going on, it's all just that upward going straight line, okay?
Yes.
What one might guess is that, yeah, in that region, the bulk viscosity is kind of small because you're off the resonant peak and it may not be that big. So it's possible that you may not actually have to worry about it too much or worry about how to get it right at all, right? That you could say basically, it's, you know, yes, there's some bulk viscosity, but it's, you know, the Navier-Stokes limit, the low frequency, the low rate, I should say, you know, the high rate, the fast rate, low frequency Navier-Stokes limit is down rather low, pushing that down that straight line. And maybe we can just not worry about it in the places we can't resolve it.
I agree. I think that that's exactly the reason, if I understood what you said correctly, I think that this is exactly the reason why there are two plots in this slide. One plot is telling you where the peak is, and so whether or not, what you have to do if you have to implement the reaction somehow. The second plot is an estimate for should I care or not.
Yeah, okay.
So that should I care tells you, okay, I am down low here. I don't care because even if I include them, the contribution to the total pressure is absolutely negligible. It won't change anything. Okay? The plot to the left is telling you whether or not this bump, this resonance bump, is into the gray or into the white area.
Yeah, okay. All right.
Can I add on to that? And it goes to answer your question as well, Mark. So, well, it's true that there will be some regions in the simulation where bulk viscosity is a negligible effect. You still have to simulate those regions. And you tend not, the general practice is to try and do the same thing everywhere, because that makes things quick. If you're trying to decide on a point-wise basis what you should be doing, then you're going to take a hell of a long time going through every single point in the simulation. So the idea is the kind of the holy grail, as it were, would be to have a one-size-fits-all. You can just do the same thing everywhere, and it's great.
I agree completely. So what I was edging towards with my question is, maybe you could do the Israel-Stewart thing everywhere, and in places where the rates are too fast for Israel-Stewart to resolve, maybe in those places the bulk viscosity isn't that significant anyway, so Israel-Stewart will be wrong, but it doesn't matter because it's not doing much anyhow. Do you see what I'm saying?
So maybe Pete wants to add on this. Yes, you can think about doing something like that, I believe. But I think that the point we are trying to make is also about what's more convenient from the numerical side. And I think from the numerical perspective. And what my understanding is that if you can choose between implementing Israel-Stewart when you can resolve the whole thing, or the electron fraction equation, say, when you can resolve the whole thing, the electron fraction equation is simpler.
Is it really though? I mean, they're both they're just both evolving one thing, aren't they? With Israel-Stewart, you're evolving this bulk viscous pressure. With the flavor, constituents here, you're evolving the electron or proton fraction. But in both cases, aren't you just adding one extra thing to evolve?
If you're doing a composition dependent simulation, you're already evolving the electron fraction. So the only thing you would need to do is modify the source term.
Yeah, okay, fair enough.
Whereas if you're trying to do an Israel-Stewart type thing, you've got to reformulate everything in terms of whatever other different thing, and then you've got a whole different set of equations that you need to solve.
Okay, I mean, I guess maybe it depends on your starting point then as to which.
Okay, yeah, if you were starting from scratch, then absolutely. Then maybe take your pick, but yeah.
Okay, are there any other questions? I want to let the audience be released when, if they've had their chance to ask anything.
Maybe there is something in the chat.
Oh yes. Yes. So Vijay asked, would heavy ions be of any interest? And Niels said he thinks it's sort of useful for flexing the fluid dynamics muscle, I think, is what he was basically saying. Yeah, this is the sort of thing that Georges Noronha at Urbana-Champaign is very interested in, and Jackie Noronha-Hosler as well. They're both very interested in taking lessons from heavy ion collision fluid dynamics and seeing if they can apply them, at least as formalism. Not obviously the timescales are totally different. The dynamics, distance scales, everything very different, but
yeah, I think that there have been some recent papers, I think, on the archive about this sort of BK, is it BK&D? I'm sure I'm going to get that acronym wrong, but
BDNK.
BDNK, I knew I was going to get it wrong, see? So trying to do that in the context of what we're doing here. And they're looking more at temperature or heat dissipation than bulk viscosity, but the kind of the starting point before you make all the assumptions is the same. Okay. So people are definitely looking in that direction. It's obviously very much in its infancy at the minute. No one's done this on big grids or anything like that. But again, I think that's an interesting avenue to explore, I think.
Okay. All right. Well, let's thank the speakers again, and we officially end exactly on the hour, which I think is an achievement we should all be
perfect.
Proud of. Thanks to the audience, for everybody for coming, and thank you for Thomas and Peter for giving us that very interesting talk. I'm just trying to think, is there anything else? Now I'm assuming